Good morning, everybody. Let's delve right into rational functions and what they are and how to graph them and just move it right along. So a rational function, just like any other rational, we're thinking about fractions, just a fancy word for fractions. And in any fraction, you can't have a zero in the denominator. So I'm going to start off with an example of some graphs. And then we're going to be able to pick apart how to make the graphs, and then we're actually going to make the graphs. So there's like 3 phases to this. So let's take a look first of all at some of the things that can happen when you have rational functions. Remember, a function means that anytime you have a vertical line, it's only going to hit in one place. So all of these particular equations will give you a graph, and they all have different ways of looking. They're not really just a parabola or just a line or something like that. There's something unique about them when you start putting a function over itself. Okay, so this one comes out to look something like this. Okay, now there are some traits about this that we're going to discuss. This one, if you'll notice, looks like a line, but it's got a hole in it. There's one value that's been taken out. And I want you to notice here that if you look, you've got a match in the numerator and the denominator as far as things that could be canceled out. So that's important, because if this and this both get canceled out, then you're left with just x plus 3. And that's what this graph looks like, but with a hole in it. And we'll discuss where that hole comes from later on. Then this one, if you'll notice, looks suspiciously like a reciprocal function, and it's got asymptotes on it, but it's not exactly like the things that we looked at before. So there are a possibility of some asymptotes showing up. There's a possibility of things looking like a line or another shape. But we want to talk about these different types of things that can happen. First of all, there's a difference between whether it's continuous or what we call discontinuous, and you're going to need to be able to recognize that. Continuous means that wherever you start drawing your graph, you can keep drawing your graph without picking up your pencil at all. It continues on and on and on as you go from one x value to another x value. A discontinuous one, if you start at a place, in order to finish it, you have to pick up your pencil and then go on from there. Okay, this one's also discontinuous because I can't draw the whole graph by continuing on. I have to pick up and move somewhere else to be able to draw it. So we've got continuous, where you could continue to draw it, and discontinuous, where you've got to pick up and start in another place. Okay, whether it's infinite or whether it's just a hole. Okay, if you have a discontinuous graph, there's a specific point or a specific place where that pickup has to happen, and that's called a point of discontinuity. So here our point of discontinuity is at x equals -2, and it's always in terms of the x value or the horizontal axis value. So the point of discontinuity here is at x equals -2. X can't be -2 because that would give you a 0 in the denominator. Okay, we want to make all these pieces make sense. This point of discontinuity here happens to be the asymptote. Once again, it's because 2 makes this a 0 in the denominator. Okay? All right. So that leads us to a discussion of the domain. Okay, remember, domain is all of the possible x values. In this particular graph, the domain is everything. No matter what you make x, nothing's going to give you a 0 in the denominator. They're all going to give you y values, so it's continuous, and the domain is all real numbers. This one that has a point of discontinuity, a point where x can't be because of this denominator, the domain is everything except x can't equal -2. And the domain here, x can't equal 2. So the difference between a point of discontinuity and the domain really is just that the point of discontinuity is what the point equals, and the domain is what it can't equal. Okay, so that's how you would express those. Okay. Moving right along, one more thing to talk about with looking at the graphs and understanding about them is that if the point of discontinuity could be fixed by just putting one point in the hole, it's called a removable point of discontinuity. So removable is the word you're looking for. So -2, 1 would fill this hole. So that tells us that it is a removable one. You could find one point that would just block that whole thing up and make it continuous. If the point of discontinuity is not fillable by a single point, so in other words, there's not one single point that you could put in here that's going to make this connect. Okay, because you're going down this way to infinity, you're going up this way to infinity. There isn't just one point there. There's an asymptote instead. That's called non-removable. And before we even get into graphing, okay, we're going to look at a bunch of rational functions. And when we're looking at them, we're going to show you techniques as far as how to find out all of this information without ever drawing the graph. And it's just the very end where we're actually going to sketch the graphs in, because this is what you use all the information that we're finding in order to do. Okay, so we know the asymptotes are the invisible lines. If there's a hole in the graph, that's a removable point of discontinuity. And we also have a continuous thing that might happen. So we need to be able to analyze these things. These are the things that you would be responsible for being able to find if you have a rational function. And we're going to go through one after the other as far as how you find them. Okay, so first of all, you should always make sure, just as a matter of a good way of doing things, make sure that the exponents are in descending order. There's a few good reasons for that, but just always do that. Okay, this is already done. And then you want to look to see if you can factor anything. Factoring is going to be super important in figuring these out. So x minus 4x plus 3, remember your factoring skills, ends up being x minus 3 and x minus 1. That makes it easier for us to find out what the domain is. In other words, everything, you always start off with everything is okay for x to be, but then if you have something that could make a 0 in the denominator, then you say, wait a minute, those points can't be in the domain. So the domain is all the x values work except x can't be 3 and x can't be 1. So that's your first step. And that one's not really anything new. Points of discontinuity come directly from this idea of domain. The points of discontinuity is just 3 and 1. It's just the numbers that actually give you zeros in the denominator. Okay, so in this case, there's not one point. There's multiple points of discontinuity. So when it asks for that, if there are multiple ones, you need to give them. So x equals 3, x equals 1. Notice these are the same. The domain is telling you it's all x except not these. These are all the values x is allowed to be. The points of discontinuity are those points, what they equal. Now, as far as whether or not it's a removable point of discontinuity or non-removable, what you look at is you look to see if there is anything in the numerator and the denominator that can be canceled out. Remember, you're looking for factors that can cancel. So here, x plus 3 can't cancel with x minus 3. There's no matches here. So since there are no matches here, we're going to be thinking about asymptotes, not wholes. Okay, I'll say that again. Because there's nothing that matches here, you're going to be thinking about asymptotes rather than wholes in your graph, which means that we are in the non-removable category. You can write this down. They're only going to be removable if the factor is both in the numerator and the denominator. There is nothing here that is a factor of the numerator and denominator. So that means that both of those are non-removable points. We're thinking asymptotes. X-intercept. Okay, you know how to find an x-intercept. You let y equal 0. So if we go back to this one and you put y equals 0 in here, you might think, oh, that's going to be difficult to solve, but not really. Because it doesn't matter what the denominator turns out to be. Because when when y equals 0, as long as you have 0 over something, you're going to get a 0 for your answer. So you don't even have to deal with the denominator. All you have to do is let 0 equal x plus 3 to find your x-intercept. Write that down. Okay, where the numerator equals 0 is going to give you your x-intercept. So our x-intercept is -3, 0. Hopefully that makes sense, because -3 plus 3 is 0, even though I don't plug it in. Okay, it's not one of our points of discontinuity. If it was, we'd have a problem, but then you'd have no x-intercept. That's a whole different thing. But as long as it's not one of the points of discontinuity where the numerator equals 0, that's going to be your x-intercept. Your y-intercept, you know, is when x equals 0. So that's a matter of plugging 0 into these. You can either plug it into the original or you can plug it into the factored form. If you plug it into the factored form, your calculations are pretty simple. Okay, and that's what I have when I pull up the slide, but let's think for a minute. If I plug in a 0 here and a 0 here and a 0 here, I'm just left with 3 over 3. So a little shortcut to that would be just, it's those leftover constants on the end divided by each other. Oops, I skipped over. There we go. So we end up with 1. Okay, you can either plug the zeros into this one, letting x equal 0 and get 3 over 3, or you can plug it into this one, 0 plus 3, 0 minus 3, 0 minus 1. We still get 3 over 3, which equals 1. So our y-intercept is 0, 1. Now, why those things will be useful is because when you're starting to make a graph, figuring out what's happening with the discontinuity, getting in your head that there's no wholes, it's not removable, so you're thinking asymptotes, and then getting in your head also where x and y intercepts are is going to be very helpful to you. We are going to hold off on doing the actual graph for a minute because I want you to completely get the hang of finding all of these things first. We're going to do several of them. Okay, this one, different thing happening here. When we look for the domain, you're looking for values that would give the denominator 0, would be the ones that they're not allowed to be, but there's no such point. Okay? There's no x that's going to make this denominator 0, because anytime you square it, whatever x you square is going to give you a positive number. So that means that x is allowed to be anything. The domain is all real numbers. This one actually is pretty easy because since the domain's all real numbers, there are no points of discontinuity. So there's not even worth asking the question whether it's removable or non-removable. This graph is continuous. Okay. The x-intercept, if we plug in 0 equals the numerator, we get x equals 5 is our x-intercept. And for the y-intercept, you have to plug in zeros for the x's. There they are. 0 minus 5, 0 squared plus 1, negative 5 over 1, which is negative 5. And there's your y-intercept. So nice and easy to find all of these, especially when you've got all real numbers. Okay, but we are having to always look at this. X squared plus 1 is also not factorable. There's nothing that cancels out. Okay. All right, let's hit another one. All right, this one's, the numerator is factorable. So we're going to factor that numerator. Okay, let's think it through for a minute. Take a quick second to factor that out. Factors of negative 4 and 1 that give you 3 in the middle. Okay, so when we look at our domain, we have to look at our original. We look at the denominator. We don't want a 0 down there. X minus 4 equals 0 would give you, your domain is anything except for 4. Oops, and I forgot to cover this, which means our point of discontinuity is also 4. So we need to figure whether that's removable or not removable. Let's think about this for a minute. X minus 4 can cancel out. So thinking about x minus 4 canceling out, that's going to tell us that it's actually a removable point of discontinuity, because you can remove it by canceling it out. X minus 4 is in the numerator and denominator. If you were thinking about canceling these out, your graph would just look like y equals x plus 1 with a hole in it. And the hole would be at x equals 4. That would be the way that that looks. If we go back up here, it would be like this, except there would be a hole at x equals 4. It's very interesting how that works out. Okay, let's go back to where I was. So this would be y equals x plus 1 for your graphing, but would just have a hole in it. Okay? And it is, we're thinking about it as being removable because there was one that could cancel out. X-intercept, y equals the numerator. 0 equals the numerator. Now there would give you 2 in this case. It would give you 4 or negative 1 being your x-intercept. Problem is that it can't be 4 because that gives you a 0 in the denominator. Okay, so that means we have only one x-intercept, and it's x equals negative 1. Okay, because there's a point of discontinuity at x equals 4. X minus 4 is part of this. You would take it into account, and if it didn't have the ability to cancel out in the denominator, it would definitely give you 2 x-intercepts, and that's fine. But in this case, we can't have that. The x-intercept is just going to be negative 1. The y-intercept, once again, plug in 0, 0, 0, and this y-intercept is going to equal 1. Or you can plug it into this one, 0 minus 4, 0 plus 1, 0 minus 4, gives you negative 4 over 4, negative 4 over negative 4, which is 1. So your y-intercept is 0, 1. Okay, so if you did want to make a quick graph of this one, okay, if we did want to make a quick graph, I'm going to do a whole new, I'm going to do a new one here. There we go. And so go. Just a very rough graph we can do. Because I want to show this, and this one didn't actually come out anywhere, but it's so nice. I can't not show it to you. Okay, so we have our x-intercept and our y-intercept. Okay, our x-intercept is -1, 0, and our y-intercept is 0, 1. So -1, 0, and 0, 1. And so our graph is going to continue and go up through those. If it's going to let me do this. Okay, so if we take a look at this graph, we had found your x-intercept and your y-intercept, and we know how to graph y equals x plus 1. The difference here is that when you have your point of discontinuity at 4, when you plug in that 4, you get the ordered pair 4, 5, once those x minus 4s were canceled out, and it gives you a hole in the graph. So it's discontinuous at 4, 5, or it's discontinuous at 4. It's a hole in the graph. And so that's a good thing for you to know, that some of them, once things cancel out, make a nice little linear graph with just a hole in it. So we have that. Okay, so what we want to do, though, after we look at this one, is we want to move on and look at, well, what happens when it's not just a hole in the graph? What about when it's asymptotes? So we're going to take a look at how to find the asymptotes. Okay, we've already found the x and y intercepts and things like that. Vertical asymptotes come from the points of discontinuity when nothing cancels out, when it's so what we need to do is we need to look for the things that give you zeros in the denominator, which in this case is 2 and 3. So x equals 2 and x equals 3, those vertical lines would be your your vertical asymptotes. Okay, your vertical asymptotes come just from using the denominator. Same here. You would be thinking vertical asymptotes at x minus 2 equals 0, x plus 3 equals 0 to find them. But the problem is that when you do that, we can do x equals -3. That's a vertical asymptote. But remember, since this one cancels out, that one's removable. So that would be just a point. It would be just a hole. So there's not an asymptote there. There's only an asymptote on the ones that can't be canceled out. All right, so here, these would be our vertical asymptotes. Here, just x equals -3 because the other two could be canceled out. Now, horizontal asymptotes are a little trickier, okay? This next slide, you're going to want to write down and have it handy throughout every one of the problems that you do, okay? And as a matter of fact, I'm going to just explain a little bit about it. We'll go straight into an example, because this doesn't make much sense if you don't have something to look at. But it has to do with the degree of the numerator and denominator, and it has to do then with the coefficients of the first term. So this is not disappearing, but I am going to add some examples down the bottom. Okay, so here's our thing that we're going to take a look at. First of all, you look at the degree of the numerator and the degree of the denominator. Remember, I said that you always have to have the exponents of the variables in descending order, and that's our standard way of writing it. So we've got a numerator and denominator. The degree here is 1, and the degree here is 1. So since they're both 1s, m equals n. So in other words, m is the degree here, n is the degree here. They equal each other. So in order to find our horizontal asymptote, this way asymptote, what you need to do is you need to look at the coefficient. Okay, the coefficient of the first term. The coefficient here is 2. The coefficient here is 1. A is the coefficient of the first term here. B is the coefficient of the first term here, 2 and 1. So your horizontal asymptote is y equals 2. So that's one of the things that can happen. So once again, first thing you look at is the degrees. If the degrees are equal, whether it's a 1 or whether it's a 5 or whether it's a 19, 19th power would be horrible. But as long as the degrees of that first term equal, the exponents equal, you just take the coefficients and put them over each other, and that'll be your horizontal asymptote. Over here, if the degree of the numerator is smaller than the degree of the denominator, that's this scenario right here, then y equals 0 for your asymptote with no additional work. In other words, the asymptote is right on the x-axis, okay, where y equals 0. The other scenario is where the exponent here is bigger than the exponent here. So if this exponent is bigger than this exponent, there is no horizontal asymptote. And no horizontal asymptote means that as it's going along, it might, it's not going to be approaching one thing. It might just go up through, and there wouldn't be any need for anything to go horizontally. Okay, so once again, if the exponents are equal, you have to take the coefficients, the numbers in front, make a fraction. That would be your y. That would be your horizontal asymptote. If this one's smaller than this one, it's y equals 0. And if this one is bigger than this one, there's none. Okay, so we're going to take a look and find the vertical and horizontal asymptotes for this, and then after that we're going to jump right into actually making graphs. So just one more to look at. Okay, vertical asymptotes. Vertical asymptotes, well, we need to factor the denominator. Denominator factors 3 and 5. Okay, these could cancel, so my only vertical asymptote will be x equals -5. Horizontally, this one is smaller than this one. So since this one is smaller than this one, y equals 0 is our horizontal asymptote. So just 2 asymptotes for the graph of that problem. Well, what does that all mean? Let's look at an example. Okay, looking at an example here. All right, I have this wonderful equation, and I want to go ahead and graph it. So I want to first find the asymptotes, and then we're going to look for some other things that we've already talked about. Okay, so first thing, we need to factor both the numerator and the denominator. You know how to factor, so I'm not going back over that at this time. Nothing is canceling out. So since nothing is canceling out, what we need to take a look at is finding vertically. Vertically goes with the denominator. So x equals -2 or x equals 2. So those would be this way. Horizontally, notice that the numerator and denominator have the same exponent. So that means we need to look at the coefficients. The coefficients are 1 here and 1 here, which is going to give us y equals 1 for our vertical, our horizontal asymptote. So vertically we have -2 and 2, and horizontally we have 1. So these are our guiding lines, our invisible guiding lines that have graphs looking like this. So you'll put them in, and then we want to find what it looks like in general. So always good when you're doing a graph to think about x-intercept and y-intercept. Okay, so x-intercept found when y equals 0, so that means our numerator equals 0. So since we're looking at numerator, then the values of x that give y 0 is -4, and the other one is 3. So we have -4, or x equals 3, is going to be our x-intercepts, and our y-intercept. Remember, our y-intercept comes from when you plug in zeros here. Okay, so 0 plus 0 minus 12. So our y-intercept is going to be +3. So we would put those points in our graph. And that's not quite enough yet to look and see what the graph looks like, but it's close. And so what we then need to do is we need to fill in some other points. Okay, find a few more points, because you want to get an idea of what the general shape is. Sometimes this middle one can kind of like go down this way. So you kind of have to make sure that when you get the graphs, you're getting what it really looks like. So pick some numbers that are near the numbers that you found. Like, for example, this is at -4. So if we plug in -3 and we do that calculation, we get -1 1/5. And we can plot that point. If I look at 0, okay, because 0 is part of my y-intercept, 0, 3, and then I pick a number to the left and to the right of it, I can kind of tell what's happening. So if I pick -1, I get a 4, and if I pick +1, I get 3 1/3. Now the thing that's good about this is it shows that it's going to be looping up here this way rather than looping down through this. And it is possible on these to have this other point be down below, in which case it is allowed to actually cross over the asymptote, the horizontal asymptote, because sometimes the asymptote, the horizontal one, is just for a section of it. And then we have 4. When you plug in 4, because 4 is right here next to 3, it's going to give us an idea of which way the shape is going. And then finally, if you connect them in, you're going to have enough points to hand sketch a graph that looks like that. Okay, so this is what you're really doing and going through here. So let me give you just one more to take a look at. Okay, here nothing cancels out in numerator and denominator. So I want you to go through, I want you to find your asymptotes, I want you to give this a good try, and then I'm going to bring up the answer and talk about it for just a quick minute. Okay, you've hopefully had enough. Vertically, we have x is 1 or x equals -4. Those are our asymptotes. Horizontally, y equals 0, because if we were to have multiplied out this denominator, you would have an x squared in the denominator. So 1 and 2, numerator exponent will be greater than the denominator exponent. So horizontally, we have y equals 0 as your asymptote. X-intercept, we would plug in and get -3. Y-intercept, we would plug in and get -3/4. Now the interesting thing on this one is we don't even have anything out in these zones. So when you were supposed to find them, you would need to actually do that. Now here's where your calculator comes into play that might be helpful. But I had to show you all the things first. If we backtrack to our last graph, I want to show you how that graph comes out on your calculator. Okay. Because your calculator's good for giving you a general idea, but it doesn't show you all the things that you need and all the things I would be looking for on a graph. So when I put that graph in and then I zoom 6 it, okay, here's what this graph looks like. So the asymptotes come out weirdly. They don't come out dashed. It actually connects that point to that point, which isn't right, and it doesn't really show you where the horizontal asymptote is exactly. So you really you can use this as a tool to get an idea. And another good thing is then you can get a table of values. This weirdo one here, okay, this is where this can be useful to you. I'm going to clear this out and pause for a second so I can put this in and not waste your time. Okay, and this graph looks even stranger on your calculator, so to get a really good idea of what's happening, you kind of do have to do it by hand and find your asymptotes and put them in. This is what that equation looked like. Watch out for parentheses on that. But what can be useful is that you can go to your table. Okay, notice on the table you've got an error here at 1, which is good because that's where the asymptote is. You can go down, you're expecting there to be an error at -4. So that's good. We have that error there. So what you can do though is you can use these values, -0.21, -0.33. If you plot a couple of them, you can get an idea of shape. Okay, and you can put those in, the ones that are going between. Okay, -3, 0, we knew that. -2 is here, -1 is here, and so it's going down like that, but then to take into account for the asymptotes, because it's got this little thing in the middle, it has to go up and it has to go this way. It has to go somewhere. Okay, and then we get to our other error and we get to see what's happening on the other side. So in this case, your table is actually more useful than your graph in order to make a good hand-drawn graph. And so that's important. All right, so this would be a good place to wrap up. Okay, hope that made some good sense to you. And Monday we'll do some quiz reviewing, and that would get you ready for your quiz on Tuesday. God bless you and have a great day.